the pre-patient get included as a center for medical image computing and UCL. If it is master at UCL with working on the field of medical imaging and toxicology with the University of Glasgow on biomedical engineering. It is interested in imaging biomarker discovery, deep learning, and progression modeling. And the title of this article is optimizing the X-ray for image analysis by identifying and removing some boundary factors.
Yeah, thank you for the introduction. Hello, everyone. I'm surprised to be presenting this work. Sorry, I have to take 21. This group is actually led by my colleague Shahab, my group, and Luke Duffy. So I help them. And yeah, I'm glad to know that you might be Great.
What is this? Microphone. All right. Yeah, sure. I'll try this. Okay. Yeah. Big data has been a prerequisite for AI models, and especially during the COVID pandemic, there was a point in which people were trying to diagnose COVID from images, just because when it hit, there was a shortage of PCR tests and all that. And basically, people collected a lot of CXRs, and what we found out is actually that using deep learning, you could diagnose people pretty well, whether they had COVID or not. But then, when you kind of examine the results closely, you saw that there's like the discriminative performance dropped when you used another data set. So what we found out is that actually there's such a big variability of data that the models weren't very reliable in the end. So we thought what would be useful to do is just assemble a pipeline for pre-processing, which I think is lacking, so that we can improve our deep learning results and analysis. Right. So here's the pipeline we came up with. So it has 5 steps in general. So it's automatic, and given a data set of chest X-rays, covered chest X-rays, the first step that it does is it's going to relabel all the data with meaningful scans, so that, I mean, by relabel, I mean give it a unique ID so that your file names are all kind of nice and neat, and they include information on the time and date of the patient, so you can distinguish which patients had multiple scans, some of them on the same day. The second step is actually removing certain chest X-rays, which are noisy or not helpful for the COVID detection, so COVID diagnosis test. So usually, there's two things I need to say here. For usual chest X-rays are done posterior to anterior, in which the patient is upright and the beam goes from their back to their front. However, in the pandemic, there were lots of scans of people where the beam went from front to back, so anterior to posterior. That was usually because the patient wasn't well enough to stand up, or the scan needed to be done in bed. So that's actually a factor that's important to acknowledge when you do deep learning analysis. And there's also several other kinds of scans, which are lateral, for example, when the patient is standing like this. Or sometimes the scan would include the abdomen as well, because the doctor wanted to see whether there's something wrong there, because there were some symptoms COVID related to the abdomen. So our pipeline is basically denoising the data set by removing unnecessary scans, chest X-rays. In this case, these are the lateral view and the ones that included the abdomen, because they're usually not very helpful for diagnosing COVID. The third step is a classifier, which categorizes chest X-ray images. Sorry, that's not a classifier. So we have a part of the pipeline is categorizing them into posterior anterior and anterior posterior. How we did that is pretty simple methods, looking at the diaphragm headers, and there's usually information there of what the chest X-ray is, what type it is. The fourth step is intensity normalization, which is basically histogram equalization so that we can increase the contrast of the image. We can see the potential opacification better. And the final step is using a model which uses an encoder together with UNet, basically, to segment the lungs in COVID chest X-rays. So we worked on the NCCID, the UK COVID-19 chest imaging database, which is a big data set that was assembled in the UK. At this time, we had 14 trusts and 52 individual hospitals. And the data set is still growing, I think. But yeah, there were patient images from patients from all around the UK. And the aim was to develop machine learning tools. Exactly. We had the task that we had was diagnosis of COVID. So we had COVID positive and COVID negative. And that was confirmed with the RT-PCR test. So that was pretty certain. And we had a total of a bit more than 18,000 chest X-ray images, or 7,600 something patients. And in terms of experimental analysis, we designed a deep learning model based on efficient net to generate just binary classification. And all of our results that I'm going to show on the next slide are based on five-fold cross validation. So we didn't have a code-out set. We just averaged across the test folds of the five-fold cross validation for the metrics. And we performed an ablation study using several steps of our pipeline to show whether we can improve our classification performance by using our pre-processing pipeline. And you can see the results here. Basically, on the left is on the top row on the left, there is an example of the row chest X-ray images. The middle is the lung segmentation. And on the right, there is the result of the pre-processed chest X-rays that we use. This is a bit of a more dramatic case, which you can see there's quite a lot of the person being visible in this, but we're focusing on the lung. And these are our results using just the raw data. And as I said, our deep learning model is efficient net B0, which is the simplest one. And we have results. You can see that using the raw data, we had an AUC of 0.72, that increased to 0.75. If we remove the noisy chest X-rays, which were the lateral scans and the abdominal X-rays that were within the data set, then only using the models on the AP or PA, so anterior, posterior, posterior, anterior data set, the AUC increased to 0.81. So that's kind of removing one more confounding factor from the model. And finally, processing the CXR through the entire pipeline, we have these results 0.88 and 0.82 for the anterior posterior and posterior anterior chest X-rays. So we're hoping to show that using a standardized pipeline that's open source and can be used on any chest X-ray, we can achieve better deep learning performance just because we're removing a lot of bias or confounding from the model. Right, these are some interesting results here, which you can see. So we'll go on this side. So on the top row here, you can see on the left, sorry, on the top row, you can see the raw images again. And on the bottom row, you can see the pre-processed images. And you can see how an interesting thing that we noticed is using GradCam, trying to see where the model focused to do its predictions. Using our pipeline actually improve the GradCam, so improve the focus of the model on areas of the lung that are actually pathological. Using the raw data, what tended to happen is the model would focus on these details on the chest X-rays, like writing or some other artifacts, which people who work with CXRs might have noticed this. So that just goes to show that having kind of more standardized data within your deep learning model helps to improve performance. And even more interestingly, I think on the bottom is actually using pre-processing can get the classification from a false positive in this case to a true negative, just because the model probably saw something within the head of the patient here or on the side or something, and made a wrong prediction, while just actually focusing the lungs in, it was able to achieve the correct prediction. And yeah, we can see switches from false negatives to true positives, and from false positives to true negatives. And it was quite good to see that it actually worked right. And to conclude, I promise to be fast and probably not as fast, is yeah, we presented this pre-processing pipeline, which I think can be used on any chest X-ray. My colleague Shahab is working on publishing the code, so everyone can use it. It basically improves dataset homogeneity, decreases bias, hopefully. And it was used for COVID, but really I think it can be used for other diseases with chest X-rays as well. Yeah, the pipeline is not very complex, as you saw. It relies on simple segmentation and dye context filtering. But that, I think, is a step that's missed by many AI experiments, just because researchers tend to focus on developing the best models without probably doing the necessary pre-processing of data. And yeah, we show that our using our pipeline improved our performance. Yeah, we hope that some of you maybe will use this. Some of you that work with chest X-rays. All right, thank you very much.
Thanks a lot for this presentation. I have one question regarding line segmentation.
Yeah.
Many interesting papers that I find last years regarding the segmentation of lung parenchyma. Actually, usually the researchers are showing the pictures when the patient was healthy, of course, segmentation of the healthy lung parenchyma.
Yeah.
Well, it's kind of easy to do that. But when you, for example, see really heavy COVID pneumonia or atelectasis, well, in that moment, you kind of see that the segmentation model doesn't know what to do.
Yeah.
What actually are the factors they should take in account? Could you
Yeah, that's exactly right. So for our segmentation model that we used, based on another person, like another researcher's work, and fortunately they have quite a cool model. You know, it's there's a paper, but they use the chest X-ray data set. COVID data set, chest X-rays, which actually had these kind of areas of classification ground glass. So there is data that they shared actually, and we trained on that data. And they also have a very interesting encoder architecture to kind of impute data and handle observations to achieve some kind of representation of this part of the lung, which is usually mistaken. So we saw quite good results in that model. It wasn't perfect, obviously, but yeah.
For example, able to all the data, for example, patients like that, is when using the concept of at all.
I don't know if we've. No, I don't think we did that. But Shahab was the main person, so maybe I can email see whether it's already case. Yeah.
I'd like to ask you, so I was wondering,
so these are chest X-rays, so just 2D images, everything is overlapped. The scanner variability is not as noticeable as with CT. I usually work with CT, so where you have different reconstruction kernels and the image can. Yeah, so the variability is whether the position of the patient, mostly the orientation of the scan, but it's basically a density-based method. Radiation goes through the image. Yeah.
okay, thank you.
Right, thanks.